Some significant cities, metropolitans, and world economic hubs sit in earthquake-prone areas. To name a few, cities like Tokyo, Japan, Jakarta, Indonesia, Manila, Philippines, Lima, Peru, and San Francisco, California are located around the Pacific Ocean, known as the Pacific Ring of Fire. The Pacific Ocean tectonic plate is in constant motion in this region, crushing and pulling against the continental plates, causing many of the world's largest earthquakes and volcanoes. This put thousands, if not millions, of people in these booming megacities at risk in an event of a major earthquake, just like the recent Turkey earthquake.
In southern Turkey, buildings crumble like sand.
Based on local and international earthquake design standards, some structures in these earthquake-prone areas are designed and built to withstand or minimize the damage caused by earthquakes. We can look at the beautiful Taipei 101 Tower in Taiwan, which is installed with an iconic golden tune mass damper between the 87th and the 92nd floor that reduces up to 40% of the lateral displacement and vibrations caused by earthquakes and wind loading. But what can be done from a geotechnical engineering perspective? My name is Chido Chashe, and today let's talk about Seismic Isolation Foundation. Welcome to Geotechs with Clements. Natural disasters do happen in all corners of the world, be it cyclones, hurricanes, tornadoes, floods, and many more. We have managed to develop measuring methodologies to predict the occurrence of these natural disasters, giving people more time to evacuate beforehand. However, earthquakes are quite different. Those seismologists can use mathematical probability models to provide a general timeline for an earthquake. There is no reliable way to accurately predict when and where an earthquake will occur. This unpredictability nature of earthquakes makes them highly devastating, which causes infrastructure losses amounting to millions and billions of dollars. Engineers have developed ways to mitigate earthquake damages in various ways. For example, methods implemented in high-profile projects like the tune mass damper of Taipei 101 or the viscous dampers of Shanghai World Financial Tower. These are more costly methods and are more suitable for high-profile, high-raised buildings. A more cost-effective technique, the Geotechnical Seismic Isolation or GSI solution, can be implemented on low to medium-raised and single-story buildings. But what is this GSI and how is it implemented?
Once finished, this 28-story building may be one of the safest places in the Chilean capital when an earthquake hits.
To begin with, geotechnical seismic isolation is a technique that isolates a structure from the ground motion during an earthquake by modifying the soil properties or introducing mechanical devices between the structure and the ground. The purpose of the GSI is to decouple the ground's horizontal motions from the structural horizontal motions. We can conceptualize the idea of seismic isolation with a building resting on frictionless rollers. When the ground shakes, the rollers freely roll, but the building above does not move. Thus, no force is transferred to the building due to the shaking of the ground. Simply, the building does not experience the earthquake. Now, imagine the same building resting on flexible pads, commonly known as seismic dampers. These seismic dampers are special devices that can absorb kinetic energy, meaning the lateral motion, and dissipate the energy as heat through their high damping characteristics, effectively protecting the structure. They work much like how shock absorbers in a motor vehicle absorbs the impact of the road undulations. A common base isolation device is a composite material of hard, durable, and flexible rubber, laminated with stainless steel plates to add a vertical stiffness, and a lead core. Japan, New Zealand, and the USA are leading countries in implementing this technology. The Ishinomaki Hospital in Japan is a great example. It demonstrated the effectiveness of base isolation during an earthquake in March of 2011. The hospital survived a magnitude 9 earthquake without much as cracking a window, making it only the functional hospital facility in that area after the disaster. Here is what a doctor at the hospital had to say.
So, can you explain the system to me?
これはですね、
Inside there is a rubber isolator which consists of 26 layers of rubber and iron sheet. It is structured to prevent the hospital from getting damaged in the earthquake by suppressing the vertical shaking and shaking sideways.
An earthquake simulation experiment was conducted in California on a 2-story hospital prototype. It can be clearly observed that the destruction is minimized even at high oscillations when the base isolation system is activated. In contrast, however, the structural components are damaged when the system is deactivated. These systems are relatively easy to install and maintain, highly reliable and robust under various loading conditions. The GSI system provides significant benefits for construction projects regarding safety, performance, and cost effectiveness. The seismic demand on structures can be reduced up to 80%, reducing the structural damage and preventing the collapse during earthquakes. There is a reduction in seismic demand on non-structural components as well, such as mechanical equipment, piping, utilities, which can improve the functionality and the serviceability of the building after the earthquakes. The construction cost is also reduced by reducing the structural dimensions and the materials required for seismic design. GSI can also lower maintenance costs by reducing the repair and retrofit needs after damage. It's a technique which is vital to societies in earthquake-prone regions. Take, for example, hospitals, fire stations, administrative buildings, and critical bridges, which have to be functional in the aftermath, where the first responders and disaster management authorities can conduct their vital duties from, therefore providing the necessary services needed to save lives. I've been your host, Chido Chasha, and if you enjoyed this video, please leave a like and subscribe to the channel. And you might as well go and check out my previous video on soil liquefaction. You've been watching Geotechs with Clemens.